Ballistic motion, the science driving everything that moves us. From medieval sieges, to baseball, to NASA's Artemis space shuttle, ballistic motion influences everything in our lives. This field of physics is imperative for engineers and scientists around the world, especially those involved in aerospace, because these equations give a predictable determination of a satellite or spacecraft's motion that can be tuned for optimal flight characteristics. Without ballistic motion, there would be no airplanes, spacecraft, radar, or any other engineering miracles that have improved life on Earth and enabled us to probe the mysteries of the deep universe. Ballistic motion, or projectile motion, calculates and describes the movement of objects on Earth under the influence of gravity. Whenever an object is moving in the atmosphere, it is attracted to the Earth's surface by gravity, which can abstractly be represented by a curve in three-dimensional spacetime per Einstein's theory of general relativity. You should go research it yourself, because the concept is actually pretty simple, but absolutely marvelous. Anyways, back to ballistics. Because the atmosphere is composed of constantly moving and colliding gas particles under pressure from the concentration of the molecules in Earth's gravity, air resistance or drag further acts to slow the object as it moves through the air, which in this case is considered a fluid. When the object inelastically collides with these particles in the air, some of the object's energy will be transferred to the particles, along with the loss of some energy as heat, which takes energy away from the object to in turn slow its motion. Between these two forces, moving objects gain their characteristic parabolic or semi-parabolic motion paths, as resistance causes their x and y instantaneous velocities to change during flight. But the projectile equations for air resistance are pretty complicated, so for this presentation I will be omitting the factor of air resistance. Think of these equations as representing motion in a vacuum. Now, onto the equations. First, let's define velocity. Velocity is speed with an associated direction and is generally represented as either initial, average, or instantaneous velocity. Initial velocity is the starting velocity of an object, or the initial force that was applied to it along either the x-axis or y-axis. The average velocity is the total displacement of an object divided by time, and instantaneous velocity is the velocity at a certain point in the projectile's flight. As a projectile is moving above Earth, gravitational acceleration acts to apply a downward force on the object at a magnitude of approximately 9.81 meters per second squared. The path of a projectile, or the shape of its parabola, is determined by the net force between the gravitational acceleration and its velocity along the y-axis. When a projectile is launched, its greatest y velocity occurs at its initial point. After that, the velocity decreases due to gravity. During the first half of its flight in the absence of air resistance, the velocity along the y-axis continually decreases due to gravitational acceleration until it reaches its vertex, while the velocity along the x-axis remains constant. At the vertex of its flight, the y velocity is 0, meaning that it is neither going upward nor downward and is stalling momentarily up in the air. But, after this point, gravitational acceleration kicks in again, and the object begins to accelerate downward after the vertex is reached due to this gravitational acceleration. The integral first step in any ballistic motion equation is to separate your v sub y from your v sub x, or your velocity along the y-axis from your velocity along the x-axis. So as you can see in the diagram above, v, or this angle represented by angle theta, this is a vector because it's an angle with a direction. And so what this means is the combination between your velocity along the y-axis and your velocity along the x-axis. So we want to separate the two. So what you can do is you can take sine of theta equals v sub y over v. And then you multiply both sides by v to where you get v sub y isolated, and it equals your initial velocity times the sine of theta. And this will separate your velocity along the y-axis for you. Then you can apply the same concept for v sub x, where you take cosine of theta equals v sub x over v, then you multiply both sides by v, so you get v sub x equals v cosine theta. And so as you can see, v sine theta and v cosine theta are both going to be lower than your initial velocity because your initial velocity is composed of a combination between your v sub y and your v sub x. And so it's going to always be larger than each of these individual values. So now that we understand the distinction between the velocity along the x-axis and the velocity along the y-axis, let's look at some equations that use these principles. So the first equation is the average velocity along the x-axis. And so as you can see from the image, the average velocity along the x-axis is equal to the change in x over the change in time. Essentially, because v of sub x always equals v sub 0x without air resistance, i.e. your x velocity always equals the initial x velocity, basically what this means is that your change in x divided by your change in time will equal the velocity of your x as an average. And so let's say that our object traveled 25 meters in 5 seconds. So change in x would be 25 meters, so we put that on top. Change in time would be 5 seconds, and we put that on bottom. And so the average velocity would be 5 meters per second in this instance. Now let's look at the equation for the instantaneous velocity along the y-axis. So your instantaneous velocity equals your v sub 0 y, which is your initial y velocity, plus the gravitational acceleration constant, which is negative 9.81 meters per second squared, times time. And so what you can see in this is, as your time increases, your instantaneous velocity is going to become smaller, because negative 9.81 times larger and larger values is going to subtract greater and greater values from your initial y velocity. So as you can see, your initial y velocity is going to slow as time goes on until it reaches its vertex, at which it will be 0, and then your object will start to accelerate downward in the opposite direction. The last of the simple ballistic motion equations we will be going over is your change in y, or your distance along the y-axis. This equals your v sub 0 y, or your initial velocity times time, plus 1/2 times your a sub y, which is your acceleration constant due to gravity, or the constant negative 9.81 meters per second squared, times time squared. This value is the integral of your velocity, but don't worry about that for now. Next, you're going to add your h sub 0, which is your starting height. And essentially, this is just a translation telling you how far above the y-axis, point of 0, the origin, that your object started, and it started its flight from. So this is necessary in order to get the vertex for your graph right. Next, you can see that we have applied this formula in the next video to the popsicle stick trebuchet that I constructed. In an attempt to model this motion, I made my own model trebuchet out of popsicle sticks. Hope you enjoy!